start lecture 16, and the course is corrosion protection methods, and today's topics will be a continuation of our discussion on materials aspects for corrosion protection. If we look back and then see previous lectures, you will see that we talked about composition effect, and we have taken reference in case of stainless steel. In fact, we have seen that by changing composition we can get several stainless steels, and when we talk about stainless steel we mainly look at the passive layer, and that passive layer gives you the protection against pitting as well as crevice corrosion. And this pitting as well as crevice, they are extremely localized corrosion mode, and there is a parameter, it is a kind of empirical parameter which suggests that what could be the level of protection towards pitting as well as crevice in case of stainless steel. So, that particular empirical parameter name is PREN. So, we are actually still in the section of composition effect on corrosion protection. So, we are looking at composition effect, and in case of stainless steel so we have an empirical parameter called PREN. So, it can be expressed as per this: percentage of chromium plus 3.3 times of percentage of molybdenum plus 16 times percentage of nitrogen plus 1.65 times percentage of tungsten. Now, this gives you an idea what could be the resistance towards pitting as well as crevice, and its full form is pitting resistance equivalent number. And if stainless steel has sufficient pitting resistance, generally its crevice corrosion resistance is also very high. So, higher this PREN, means higher pitting as well as crevice corrosion resistance. And that is why we add a little molybdenum as well as nitrogen or tungsten to get a very good pitting resistance. Of course, chromium is always there. So, this is about the PREN, but remember this particular PREN it gives you a kind of idea, general idea, but there could be a possibility that higher PREN may be having lower pitting resistance, because there are other factors like precipitation of manganese sulfide or precipitate free zones or chromium depleted zones. Those can be possible if we follow a faulty process or if we have inhomogeneous alloy. Those are the possibilities. Okay. So, but it gives you a fairly good idea about the stainless steel's resistance against pitting and corrosion, pitting and crevice corrosion. Now, this is about composition effect. Now, if we see that composition and microstructure as well as processing, at times we will see that it is very difficult to distinguish the effect of each one of them separately. So, like one more factor that can contribute to corrosion protection is the ease of attainment of passivity. Okay. So, if we look at that particular part, that ease so if we consider this, in case of passivating metal, of course environment also comes into picture. So, there if a material alloying or the alloying is done in such a fashion that the material goes from active state to passive state quickly, and then we will definitely have a very good corrosion resistance, because once passivity achieves, we have corrosion in the passive zone, which is a very low corrosion current density. Now, for that we have to also look at two aspects. One is composition. We can say that alloying effect, plus change in microstructure. So, these two effects can be considered together. Now, the choice of alloying element will be decided, since we are looking at the passivity, will be decided on the basis of the element or the alloy what we are talking about. For example, in case of chromium or titanium, if we add little platinum or palladium, we can get spontaneous passivity. Okay. So, and also it happens when there is hydrogen ion reduction, but there are no oxidants present, strong oxidants. Oxidants are like oxygen, dissolved oxygen, or some other strong oxidants like ferric chloride or Fe+3. So, then this effect might be different. So, in case of chromium or titanium, so this particular combination of alloying as well as change in microstructure would come into picture. Now, we have chosen these two elements because these two elements show active passive behavior. Now, depending on where the cathodic polarization line cuts the active passive zone of that particular metal, we can get either active zone or we can achieve spontaneous passivity. In fact, we can also get unstable passivity also. We have seen before. So, what happens in case of active passive material? Let us say we have this diagram E versus log I. Here it is ampere per centimeter square, let us say this is voltage. Now, this material shows active passive behavior. So, that means this is my equilibrium potential for chromium. So, it goes like this, then so this is a typical active passive metal. So, this is my active zone, this is equilibrium potential for the metal, and this is my I0 for that metal, let us say titanium, and up till this zone, this is anodic, everything is anodic on top of this particular point. So, this is active and then beyond this point to this point, this is passive, and then beyond this point we have transpassive. Okay, let me just put it in strong color. In fact, if this zone, this particular zone, there could be a possibility of a kind of a slant line. This slant line is possible. So, then there could be one more zone. So, from here to there is basically a transition zone, fine, from active to passive. Now, where the polarization line for cathodic reaction cuts this anodic part, that would decide whether this material will show active behavior or spontaneous passive behavior. Now, if the polarization line for some cathodic reaction, let us say this is my point. So, let us say this cuts this line here, bypassing this particular point, it bypasses this point. So, that case, and this is my, let us say, hydrogen evolution reaction. Okay. We are talking about cathodic polarization, and this particular part is titanium So, here titanium is actually dissolving in the form of Ti3 plus. So, we have this is the point corresponds to I core and this is corresponds to E core. Okay. And the plot will be, if we do polarization, the plot will be like this. And if we continue this polarization till this point, but if we keep continuing the polarization, then plot will look like this, like this. So, this will show typically active passive. So, if we continue till the end of active zone, that means till this active zone, then we will get this. Okay. And then the material will corrode as per this I core, what in the red color what has been shown. Now, this particular hydrogen polarization line, hydrogen evolution line, if it cuts across this, if it cuts like this, okay. So, this is my hydrogen line now. So, that time my polarization plot would be in this particular same diagram if we want to show it. So, it is cutting at this point there. So, the schematically I can show that, I think this one I can drag it little down, okay, like this, but when it okay. So, now when it cuts here, so then plot will be in that passive zone it is cutting now. So, the plot will look like okay. So, like this. So, that means this is spontaneous passivity and this is active. Now, if we see that if we convert this polarization behavior from active to active passive and then going to spontaneous, so then definitely my corrosion rate will be much lower than in the active zone. So, here you could see that in this case my corrosion current density would be I core, and I can put it passive. So, this is much lower than I core, which is this one. So, then corrosion rate would reduce drastically. So, this can be done by introducing platinum or palladium in a small amount in titanium and chromium, and since we are considering only hydrogen reduction reaction, so this is applicable in case of acid solution. Right. Now, what is done in case of titanium? Let us say we add little bit of platinum. Now, before we understand the behavior of that alloy, let us understand the mixed potential theory in case of connecting platinum with titanium, fine. And we know that hydrogen evolution exchange current density I0 hydrogen evolution on platinum surface is much higher than I0 hydrogen evolution on titanium surface. And here if you consider this I0, so this is my I0 hydrogen evolution, and this is basically on titanium surface. Now, when it happens like that, so you are going into the section of mixed potential theory. Initially, it will have its own anodic and cathodic part. This is my I0 titanium, sorry, this is E equilibrium, and this is I0 on titanium surface for titanium. This is the anodic part where titanium is dissolving. So, this is titanium minus 3 equal to titanium 3 plus. Now, let us say on titanium surface, the hydrogen evolution reaction is like this. So, this is hydrogen minus H plus minus electron equal to H plus, and this segment is, so this hydrogen evolution, and this is E equilibrium for hydrogen, and this corresponding point is I0 on titanium surface, that is hydrogen evolution exchange current density, and we know that I0 is exchange current density E equilibrium is equilibrium potential, and this is non-corroding. To understand this, I would request you to go back and check the earlier lecture series. Okay. So, correspondingly, that whenever I am putting this subscript titanium, that means that exchange current density is on the titanium surface, and one case it is titanium dissolution or titanium deposition on titanium surface, that time one exchange current density which is a non-corroding condition. And similarly, when I am writing I0 H plus slash H2, that means we are considering hydrogen reaction on titanium surface. that the subscript is basically the metal on which hydrogen reaction is taking place, or metal dissolution or deposition is taking place. So, that is the connotation here we are using, identity. Now, when we are having only titanium, no platinum. So, now we are having, this is a titanium plate, we are adding another platinum plate and connecting it. This is titanium and platinum. So, this is galvanically connected, and this is acid solution and no oxidant. Okay. So, that case, since we know that this is the situation whenever we add titanium with platinum, that would galvanically connect, my equilibrium potential will not change. So, that means this will remain fixed, because this is decided by the Nernst equation as well as pH of the medium. So, that would not change, but exchange current density on the platinum surface would change and it will progress to the right. So, it will go to this place. So, this is little higher up. So, this place it will go, and it will have its own polarization. So, that means, so this is positive polarization and this is the negative one. Okay. So, this is hydrogen plus E equal to H2 half H2. So, this is basically I0 hydrogen evolution reaction on platinum surface, fine, and this is H plus, sorry, H minus E equal to H plus, which is basically the anodic part for the hydrogen reaction. Since it is mixed potential, so that means we have to add up this current with this current density, and this is in the current density axis log I. So, if we add it up, so it will go like this, or let me put a different color. So, red color. So, this is my combined cathodic polarization. It includes two currents on titanium plus on platinum. So, on platinum hydrogen evolution and on titanium hydrogen evolution, that two currents are added, because this is coming from mixed potential theory. This is coming from mixed potential theory. Okay. So, now if we see that the junction point where this cathodic line is cutting the anodic portion of titanium is at this location, So, previously it was cutting here, now it is cutting as shown by green arrow. Now, the current density corresponding to the corrosion rate for the new situation, which is the galvanically coupled titanium with platinum. So, that current density is I can put I core with adding platinum, which is in combination of platinum, and this particular current density, which is I core only with titanium. So, here platinum means basically it is a coupled log I. Okay. So, now if we do polarization, then we will see the exactly similar plots here. In this case, what we are doing, we are changing the, in this particular case, we are changing the cathodic polarization kinetics. So, in case of brown line, in this particular case, this brown line is actually coming with a much shallower slope, that means its kinetic is enhanced, but here kinetics of hydrogen reaction on both the plates, titanium as well as platinum, both are same because that slope is not changing. But what's happening, because here the exchange current density of hydrogen evolution on platinum is much higher than on titanium. That's what we are moving from active zone to spontaneous passive. So this would lead to spontaneous passivity, and this is this particular segment, this particular coordinate is active behavior, active, no passivity. So that means if you leave titanium in acid medium, then it will dissolve at this rate, okay. And if we have platinum connection, then it will dissolve at this rate, okay. And at the same time, if you notice I core titanium platinum, that couple is much less than I core on titanium, okay. So when there is no coupling, and since this is in the log scale, so that difference would be few orders of magnitude, and the polarization plot would be similar like this. So in this case, in one case we will get active behavior, another case we will get on the same plot. If we try to plot it, E versus log I, the plot pattern would be, okay. So this is spontaneous passive and this is active. So if we don't do any polarization study, titanium will corrode as per this corrosion rate, and if we leave it with the connection of platinum, it will corrode at this rate. This is this particular rate, okay. So there will be huge reduction in corrosion when we connect it to platinum. So this same concept is taken up for alloying. Now when we alloy, little bit of platinum is alloyed in titanium. This is the alloying. So it is a homogeneous mixture in the beginning. Everywhere we have platinum homogeneously distributed in titanium in a solid solution. Now once it is exposed to acid medium, then one particular thing happens, because platinum sits very high up in the reduction potential series compared to titanium. So titanium is much below platinum in reduction potential series. So platinum has got a higher reduction ability than titanium. So once it is exposed to acid, in the beginning platinum and titanium both will go in the solution in the form of ions, but since platinum ion has got a higher reduction ability, so it will deposit back, and on titanium there will be small platinum pop-ups. So these are some platinum pop-ups. Okay. Now the similar mixed potential theory can be followed. So what we have followed here. So that means on platinum now hydrogen evolution would start because it is acid medium, and the polarization line, the mixed potential polarization line for the cathodic reaction will cut the titanium polarization line in the passive range, and then immediately passivity will be achieved. In the beginning definitely the corrosion would be very fast for titanium, because the path for the reaching to this passivity, spontaneous passivity, is this one. So it goes like this. Okay. So this is the path. So that means initially it will have a fairly good amount of corrosion, but it will happen for a moment, and then once it reaches to that particular passive point, which is the point of spontaneous passivity, and immediately we will see that the platinum dissolution rate will go down to a great extent. Now, this is, I think this is a very smart way of alloying. So, in this case one should take care that there should not be any abrasion on this surface. So, on this surface if we have abrasion, or let us say somebody rubs it off, okay, so then there could be an issue, because all those platinum spots will be out and immediately it will get back to the situation what we had here. Okay. So, from here to this, that situation can arise if we rub off that particular top surface. Interestingly, this is actually a combination of microstructural modification, in situ microstructural modification. So, initially it is homogeneous, fine, and whole body is homogeneous, at the same time surface is also homogeneous. So, both surface plus body. Now, in this case, after, because of this dealloying effect, so this happens by dealloying plus redeposition of platinum. Okay. So, because of its higher reduction potential, so platinum ions will get reduced back on the surface of titanium, and then we will get those platinum spots on top of titanium surface. Now, here what we see the change? We see the change like it will be homogeneous in the bulk, but heterogeneous on surface. In fact, surface texture also different. So, we are changing surface microstructure plus physical texture. So, that means appearance of the surface. So, these two are changed. So, it is a combination, this particular effect is combination of alloying plus surface change, surface microstructural change. So, this is also possible in case of chromium, but remember we should not have any oxidant. But interestingly, this alloying should be very carefully done. In case the polarization plot is like this, schematically I am showing log I, this is E. If it is iron, then iron also has a kind of plot like this, okay. So, this is typical active passive behavior iron shows, but there initially iron on iron surface, this was my cutting point for hydrogen evolution reaction. So, this is again in acid in case of iron. So, there if we put platinum, this potential is basically between this point and this point. So, on platinum surface, as we have seen from the mixed potential theory, so this is on iron surface, hydrogen on iron surface, this is I0 hydrogen on platinum surface. Of course, the mixed exchange current density of hydrogen on platinum is much higher than that in case of iron. So, it will have its own mixed potential. So, this will be my corrosion rate, new corrosion rate for iron platinum couple, and this is for only iron. Okay. We could see that I core, so this is my I core iron platinum, this is much lower than this. So, that means if we alloy it here with platinum, we are going to increase the corrosion rate few orders of magnitude. So that means we have to be very careful for doing such kind of alloying. First we have to have a proper idea of its polarization behavior in that particular solution, fine. And if the such situation arises, we must not do any noble metal alloying. In fact, there also the same principle would work. Homogeneous, initially it will be homogeneous and then dealloying and de-deposition of platinum, because of platinum higher reduction potential of platinum ion compared to iron ion. Okay. So, iron will dissolve and then platinum will deposit back, and similar situation can arise what we have seen in case of titanium. So, there it will be catastrophe because the corrosion rate would increase enormously. So, this alloying we have to also be careful and do it after doing a proper laboratory test, and then finally we should go ahead. So, this is about the smart choice of alloying element. At the same time, what we are seeing, we are actually trying to get the material to a spontaneous passive zone, and we should make such alloying so that the passivity achievement becomes very easy. So, that is what we have termed it as ease of achieving passivity. So, this is one such example for the effect of microstructure as well as composition. Okay. So, let me stop here. We will continue our discussion on the effect of metallurgy on the corrosion protection. Okay. So, till then, thank you.